Hey everybody, I think we're going to get started. So I am Adam Forsyth, and I am a group engineering lead and community lead at Braintree. Some of you may know that Braintree and Venmo are the same company. Venmo is one of the sponsors here today. They are recruiting. Unfortunately, the recruiters couldn't make it today, but please check out the booth, grab a business card, or talk to me. Yeah, so one important thing to know, in addition to the title of this talk, which is Beating Mastermind, is that the code, the slides, and even my speaker notes will be posted on GitHub after the talk. So the slides don't have a lot of content. A lot of it will just be in what I say. But all that is available online, so don't worry about catching every single thing. So this talk is about a game called Mastermind. But it's really about being comfortable with algorithms and being comfortable with academic papers and being able to take a simpler academic paper and turn it into code using just the normal resources you have available to you, like Google. And I am going to talk a little bit about one specific algorithm called Minimax. So what is Mastermind? It's a two-player code-breaking game. One player creates a pattern and hides it behind a screen, which you can see on the bottom left. And that person is called the code maker. And the other person guesses that code and gets feedback in the form of black and white pegs. And that person is the code breaker. And it's based on like a century-old pencil and paper game called Bulls and Cows. No one knows exactly how old it is or where it came from, but it's at least 100 years old. So here's an example game, and I'm going to walk you through it. The secret pattern would be at the bottom of the screen, but hidden from you in this example. And it's off the screen here because it's not important. And so the guesses start from the top. So in this game, I started out guessing 4 reds, and there's no colored in circles on the side. So there aren't any reds in the answer. I then went to 4 yellows, and got 2 black circles on the side representing 2 black pegs. So that means that there are 2 yellow pegs in the answer. So that's great. Getting going here. So I try guessing 2 yellow and 2 green. And now we see we have a white peg. And that means that there is still 2 yellows, as we already know, but one of these yellows is now in the wrong position. So if you have the right color but in the wrong position, you get a white peg. Right color, right position, you get a black peg. And as we only have 2 pegs, we know the greens are both wrong. So I then try different positions for the yellows, and I get lucky here. I have 3 black pegs, and I know that 2 of those represent the yellows, so both yellows are in the right place. And then I have 1 black peg for one of the blues. So blue, it turns out, is also a color that's there, but only 1, not 2 of them. So I keep one of the blues and add an orange, and so I still have 2 black pegs for the 2 yellows, but now I have a white peg for the blue, which means that the blue is now in the wrong position, and orange was the wrong guess because there's still only 3 pegs, not 4. And finally, I switch out the orange for purple and swap that purple with the blue. 4 black pegs, I win. So this is a pretty normal game. It took me 6 guesses to win. If you're a beginner at the game, that would be really, really great. If you've played it a lot, that's sort of normal. Yeah, so the screenshot I just showed is from this really cool collection of puzzles online called Simon Tatham's Portable Puzzle Collection. They were originally written in like C or C++ and compiled, rewritten in Java, and then transpiled to JavaScript, so you can play them right in the browser on his website. They're really great. They're all logic puzzle games, and there's a ton of them. They do use non-trademarked names, so that Mastermind is called Guess on this page. But running into Mastermind on this page after having forgotten playing it as a child is what led to this work and this talk. I was hoping to use more screenshots from the game from this website, but unfortunately, due to time, I have cut those, so not quite as important as this would have been otherwise. So let's talk about the paper that we're going to go through here. It was published in the Journal of Recreational Mathematics in 1976. It's called The Computer as Mastermind. And it was written by Donald Knuth, who is a very famous computer scientist. He's known as the father of the analysis of algorithms. He created the text typesetting system. And he wrote The Art of Computer Programming, which is a huge multi-volume reference book talking about all sorts of numerical programming. And in this paper, he gives a solution to Mastermind that always wins in 5 moves or less. So it always, every single time, does better than we just did in our example game. Unfortunately, he gives the solution in a format that looks like this. It's a giant table of numbers, commas, parentheses, colons, And it just doesn't really mean anything when you first look at it. And this isn't even the whole thing. This is just the first half. It covers 2 pages in the journal. And he does, luckily, in the paper include a very brief description of how to use the lookup table. But it doesn't this doesn't tell you anything about why this table works, how it works, or anything about the structure of the game we're trying to solve. And we're programmers, we want to understand it. So we actually, unfortunately, have to read the paper. We can't just go off the solution. And there just isn't any code. There's no code in the paper at all. I don't know why he would give code. This was in a recreational math journal. Not a programming journal, but still, it would be nice. So the paper has several sections. These aren't like labeled in the paper, but this is roughly its structure. And we're just going to go through the first few here. First, it describes the game. We've done that. It explains how to use the lookup table. We don't care. We want to understand it. We don't want to use the lookup table. Then it gives several examples of working through the lookup table. And this is a little important because in these examples, he uses the numbers 1 to 6 instead of 6 different colors. So we're going to do the same thing when we write our code, and we're going to talk about these the solutions or guesses or answers or whatever as numbers 1 to 6, basically. So 1, 1, 1, 1, 6, 5, 3, 2, things like that. So I'm going to jump now to part 4, where he talks about choosing impossible answers. So I'm just going to read this, which I know is a little boring, but it is important to understand for understanding our code later. Incidentally, the 4th move, 1462 in this example, is really a brilliant stroke, a crucial play if a win in 5 is going to be guaranteed. None of the 7 code words which satisfy the first 3 patterns could successfully be used as the 4th test pattern. A code word which could not possibly win in 4 is necessary here in order to win in 5. So what this is saying is sometimes we'll need to guess a combination of colors that we know to be impossible in order to eliminate enough of the problem space to win on our next move. And if we don't do this, it would sometimes take us 6 moves to win, which is exactly what we're trying to avoid here. We're trying to win in as few moves as possible. So this is pretty cool. It's something that a human player would be very unlikely to do intuitively, and something that I had never done when playing the game myself, well, at least on purpose, before reading this paper. And just for reference, I can win every time. I never lose when I play Mastermind. It is possible as a human to come up with your own algorithm that's good enough to always win, just not always in 5 moves. So that's cool. So let's go to immediately the next paragraph in the paper, which is part 5. And this is really the heart of the paper. So yeah, focus is good here. Figure 1 was found by choosing at every stage a test pattern that minimizes the maximum number of remaining possibilities over all 15 responses by the codemaker. If this minimum can be achieved by a valid pattern, making 4 black hits possible, then a valid one should be used. But subject to this condition, the first such test pattern in numeric order was selected. Fortunately, this procedure guarantees a win in 5 moves. Okay, so I don't think this is stated as clearly as it could possibly be. When he talks about 15 possible responses by the codemaker, he means that there are 15 different combinations of white and black pegs you could get as your feedback. It doesn't mean you're going to get 15, just that there are 15 possible ones. And that'll differ depending on how accurate it is. And you want to pick the guess that most reduces the number of correct answers left, given that the feedback that you receive for your guess is the one that gives you the least information. So if you picked 1, 1, 2, 2 as your pattern, and you got like 2 white pegs, let's assume that's your worst case. That's still going to leave you with like 150 possibilities or something. What you're trying to do here is minimize the number that the worst case response is going to give you left, because you don't know what response you're going to get to your guess. It's unknown to you, so you have to just try and look at all of them and see which one's best. So just let's focus again on those words. And the emphasis that you see on the screen is in the original paper. That is not my emphasis. Minimizes the maximum number of remaining possibilities. So yeah, it then describes how to break ties, that you pick a valid pattern, one that could be the answer itself, if possible. But if not, you select one that is impossible, because it's better to select one that's impossible and still win in 5 moves than win in more moves. So, and then subject to that, you just sort them numerically. One of the advantages of using numbers instead of colors to represent them is that we can just use that as a tiebreaker. Pick 1, 1, 1, 1 over 1, 1, 1, 2. So we need to figure out how do we implement that. And of course, the answer to figure out how to implement that is just to Google it. We all know that already. I'm not telling anyone a secret. So I literally, if you Google, even if you just Google maximize minimum in the first page of results, you're going to get a Wikipedia article titled Minimax. And I Googled maximize minimum algorithm, and it comes up even higher on the page. But for those of you who don't like Wikipedia and who like Stack Overflow instead, don't worry. Several of the top answers are also on Stack Overflow, and they're not quite as direct a route to getting the code you need, but they still help you. So it's fine. You want to use Stack Overflow instead of Wikipedia, feel free, just so long as you Google it first. So I'm not going to go into the exact definition of minimax. It's pretty much what we've just described. If you try and minimize the maximum value, you can just read the Wikipedia article if you want to know more. But since we're impatient programmers, if you look at the table of contents here, you'll see down near the bottom there's an entry that says pseudocode, which my eyes certainly went right to, probably everyone else's. We're just going to skip down to that, section 2.2, and hope it points us in the right direction. This is my process a lot of times when I'm doing this kind of thing, right? You just accumulate enough little bits of information to get there, and then once you have code that works, then you really try and understand the problem. It's not always the right way, but it can be great. So this is really short. That's really promising. I've done things like this before and found links to more academic papers that link to more academic papers. That doesn't happen here. We get a nice short snippet of code. So let's just walk through the whole thing. We're going to start from the very first line, the function parameters. The node is just where we are in the game. It's what we've already eliminated, what our last guess was, and what score that guess got. The depth is how much further ahead in the game we want to look to see which guess is best. And just if you remember, in section 5 there, it said, look ahead a guess and the scores that guess would get and pick the best one. So that's 2 depth. So we're just going to look ahead 2. So that's our initial depth when we first call this function. And we're going to ignore the last parameter just for a second. So let's look at the second and third lines. If the depth is 0 here, we've already looked ahead, and we just need to provide a value for our guess that will tell us what its score is, how good it is at helping us solve the game. And in our case, we're never going to reach a terminal node before we reach depth 0, so we're going to ignore the second half of that if statement. And again, remember from part 5 of the paper, the heuristic for a score from the code maker is the number of possibilities. I think, yeah. So I think I'm stepping on the audio cable. Yeah, so we want to make sure that for when we're running through this for the code maker, for the person providing the score back, not the person guessing, that we give back the number of possibilities related to that score. And when we're going through it for the person who's guessing, the heuristic is what was given in the paper. It's that number that we got from the score. It's whether or not the guess itself is valid. We prefer valid ones over invalid, but we'll take either. And then finally, the guess itself, right? Numerically, 1 to 6, 1, 1, 1, 1, 3, 4, 1, 2, whatever it is, to break ties. So those are our heuristics. So now let's look at the middle part. We want to think of ourselves as the code breaker here. We want to minimize the maximum. So the code breaker, the guesser, is the minimizing player, and the code maker, who wants to maximize the problem space left, is the maximizing player. So the child nodes are the possible scores that a guess could get when we're talking about the maximizing player. Those are the moves of the maximizing player, are the scores. So for the maximizing player, we look at all possible scores and we take the maximum heuristic value, which, as we just said above, would be the number of possibilities that that score would leave. So let's look at the last few lines now. The minimizing player, the else block down there. And the child nodes are the possible guesses that we could make as the code breaker. And so we take the minimum of the heuristic values that were returned by the next depth down in the function calls, which was the maximizing player. And so if we start from our first call to the function, right, we first look at each guess and then call the function again for getting scores. And then we look at each score and look at the number of potential answers. And then we go back out a level and take the maximum of those number of potential answers with the scores. And then we go back out another level and we take the minimum of those maximums. And that's our result. So I know that was a lot, and it'll be easier when you see the actual Python code. But at this point, we've done all the hard work, which is good because we're 15 minutes into a 25-minute talk. We've read the paper and ignored its crazy lookup tables and understood what it's actually trying to do. We've looked up the algorithm on Wikipedia and read the pseudocode and understand it. And now we just have to implement it. And specifically, I'm going to implement a version of the game that just plays against itself. It generates a random answer, uses the Knuth algorithm to solve it, and repeats. Don't worry if you don't follow every line of this code exactly. Like I said, this is all online. The code will be there, the slides, the speaker notes, so you can always go through it at your leisure. This code could be structured better, and it was originally, but I've shortened it and sort of taken out some more advanced Python features and stuff to make it a little easier to follow for the talk and just to fit on the slides. And so as a result, it's boiled down to actually just about 60 lines of code after all of that. So not a ton really longer than that pseudocode that we saw, even once we've folded in the specifics of our case. So first I'm going to show you the general logic that you need for Mastermind. When we start a new game, we need to set up a few different things. First, we say we haven't made any guesses yet, 0 guesses made so far. And then we're going to generate a random answer. We look at the numbers 1 through 6. We grab randomly one of those 4 times, squish them together in a tuple. That's our answer. And then we set up some things we need to solve our algorithm. We make a set of all the possible scores, which of course at the beginning is all possible scores, and a set of possible answers, which of course at the beginning is all answers, as we haven't eliminated any yet. And I'll talk about those in a little more detail when I get to how we're going to implement the algorithm. So here's the main loop of the game. You can make up to 10 guesses, so while we haven't made 10, we'll keep going. We'll call our function that makes a guess, which of course we'll see again in more detail in a second. And if that guess is valid, if it's in the list of all possible answers, then we'll increment the number of guesses made. We don't want to penalize people if they have a typo, if you're maybe doing an interactive version of this or something like that. And then we calculate the score for that guess based on the actual correct answer. And again, we'll see that in more detail in a second. And if the score is 4 black pegs, 4 Bs in our code implementation and in the paper, then you've won, and we'll print out the number of guesses it took and what the right answer was and break out of the loop. Now you'll notice here, I don't actually handle the case where you lose. Luckily, we don't need to because this algorithm always wins. But I promise that while I was actually writing this code, that I did have that branch there and it printed out a ton of debugging information so I could figure out what I did wrong. So while you're writing it, and handle the loss case. But once it's done, you can delete that because it's never going to happen. So again, just to keep the code a little shorter. Cool, so this is how you calculate your score. Hopefully after seeing the example and hearing me talk about it, you have a general idea how it works. But we set up some empty lists to keep our score as we build it up. Our wrong guess pegs, meaning pegs that were in our guess but aren't in the answer, and then vice versa, pegs that are in the answer and not in the guess. So we go through the pairs of pegs that are in the same position, like the first, second, third, or fourth position. And if they match, we get a black peg. And if they don't, we store them away for later. And then we go through them a second time, checking if any of our pegs that didn't match exactly match a peg that was in a different position. And if so, we remove that peg from further consideration and give ourselves a white peg in our score. And then we just return that as a tuple, and that's the result of this function. So finally, we now need to set up our initial information we need to run the algorithm. And this part is actually a little slow. It takes like more than a second on my laptop, like 5 seconds or something. So we're going to do it once in the init function of our class. And that way, we can run the game over and over and over again and only do this once by just calling the play method many times. So we generate the list of all answers, which is just all combinations of the numbers 1 through 6. It's like 1,296 combinations. We then set up a list of all possible combinations of guess and answer and what score they would get. So later, when we need to know the scores of things, we don't have to calculate it, we just look it up. And this is a little duplicative, right? Because you have them in both orders, and you have if they exactly match, it's calculating the score, and you just know it's going to be a win. So this could be more efficient, but it's not that slow, so we're not worried about it as long as we're only doing it once. Yeah, so finally, the climax, we're going to implement our algorithm. If we've made guesses before is the very beginning of this function. So we're not talking about our first guess here, just all following ones. We're going to look at all the possible answers and see if they're still valid given the score we got on our last guess. And if they aren't valid, we're just going to throw them away. But if they are valid, we're going to keep going. And we're going to set up an empty list to keep all of our heuristic scores for all potential guesses that we're going to then take the minimum of at the end. So this is really the meat. So we again filter the list of potential scores to filter out answers that are now impossible. We never filter out a guess, because remember, we might want to choose an impossible guess, but we do filter out answers we know aren't possible. We store it again for later. And now we're descending down into our function. So we calculate all of the line that says collections.counter is counting how many times each score appears. So how many possible answers that score represents. We're taking the maximum value, so that's our heuristic for the maximum, for the maximizing player. And then we're checking whether or not the guess itself is possible, and we're appending that number, the maximum number, whether or not the guess is possible and the guess itself, onto our list. Finally, we sort of remember we're in a branch, and so after we return that minimum to get out our guess that had the minimum heuristic value, we also need to handle the first move. And the first move is just 1, 1, 2, 2, or 2 of one color and 2 of another. And this just happens to be the only first move that guarantees a win in 5 moves or less. And it's sort of hand-waved over even in the paper. You just try all the combinations till you find one that works, is I think what Knuth did in order to come up with that. But if you ever spend 20 hours or something playing this game without reading this paper, you would come to the same conclusion. It's not too hard. The game's not that complicated. So finally, if we have just a minute, I would like to show you the code running. I think we are actually out of time, unfortunately. So you'll have to download it and run it yourself. It just runs in a loop, takes 5 seconds the first time, half a second after that, and spits out a bunch of answers and wins every time in 4 or 5 moves generally. So unfortunately, we don't have time for questions. It'll be on my GitHub, github.com/AGFOR. And yeah, come find me after this if you have questions. Thanks a lot.